Okay. So last time we started with the lecture on basic concepts of meta-heuristics, and we just briefly started talking about these design concepts. Okay, so main design concepts. First of all, we mentioned that the representation of potential solutions. So how are we going to represent a certain solution? We'll look at different types of representations, which then we can use as a basis for designing a search algorithm and different move operators and so on. So we need to decide how we're going to represent potential solutions to our problem and how we're going to define the fitness or the evaluation function. This fitness function is going to give us a specific value that will indicate the quality of a particular solution given its representation. So we want to be able to compare any two solutions and say which one is better. So we need some kind of a fitness or an evaluation function that is going to guide our search. Okay, let's look at different representations. So the solution representation or the encoding is a critical design issue. What are some key things that we need to keep in mind? And I'll get back to this also later on. So first of all, we need some kind of efficient representation that we can then later manipulate when we specify certain search operators, such as there are these different neighborhoods. For example, if we say that our representation is a binary vector, and we might want to define a search operator as being solutions where we're going to flip certain bits of the solution to obtain new solutions and so on. Or we want to, if we have some kind of genetic algorithms, keep in mind how we're going to recombine, design certain crossovers, and so on. So we need some kind of a solution representation which allows our meta-heuristic to be efficient and effective. Of course, it has to be suitable and relevant to the problem that we're so what kind of a problem are we trying to solve? Are we looking at permutations? Are we looking at real values, binary values, and so on? And of course, many alternative representations are possible. The idea is to find one that is most efficient. So we might have, let's say, a two-dimensional array, a single vector of fixed length, variable length. So we'll look at some various examples. This is obviously one key issue that you need to decide when you start off with designing an algorithm is how you're going to represent the solution. Okay. The necessary characteristics of a valid solution representation. First of all, completeness. So we want all feasible solutions of the problem to be able to be represented. That's the first thing. Connexity or connectivity means that we want to be able to design such a search path between any two solutions in the search space. So this, if I give you any solution, there has to be a way to obtain any other solution in the search space, which also then includes the global optimal solution, no matter what the initial solution is. So we have to be able to somehow traverse the search space and obtain any solution in the search space. So this is a key thing. And efficiency, the representation can easily be manipulated by search operators. We need to keep in mind how large the search space is, and we'll look at examples of how we can, based on the choice of representation, decrease the size of the search space, and this is a key issue. Okay, before we get to some examples, just two more things. So two main classes, let's say, of representations. Most often we're looking at some kind of a linear representation, which is a string of symbols, and such as a binary vector, a vector of discrete variables, real variables, permutation vectors, and so on. We could also have some kind of a nonlinear structure, such as a graph structure. So this is not a typical representation, but such examples are used, for example, for encoding regression problems, where, let's say, you're given some kind of an input and output values, you're trying to find a function that will best output, that will provide the best output given the inputs. So, for example, let's say if I have a if I have some kind of a tree structure where at the root of the node I have a node that says multiply, and then I have certain branches that say add, subtract, and further branch certain variables. Again, trying to draw, this is not working. Sorry. Okay, anyway, I'll show you some examples in future lectures of these nonlinear structures, but now I'd like to now actually focus on these linear structures. Okay, so one example is a binary vector. So a simple example where if we have any decision variables that represent either the presence or an absence of a certain variable, such as a yes/no decision, for example, the knapsack problem, whether a certain element is picked or not, 1 or 0, satisfiability problem, whether a certain variable is assigned a true or false, any kind of binary integer problems. Such a solution can be represented as a vector, as a binary vector. Okay, so as I said, for example, xi is 1 if an object is packed or picked, 0 otherwise for the knapsack problem. A more general approach would be binary encoding, where this decision variables can be assigned any value from some kind of a discrete set of values, some kind of alphabet. This we can use mostly for combinatorial optimization problems where we have a certain set of possible values. Examples are location problems, assignment problems, IP problems, so integer programming problems, location problems, again, trying to see or indicate at which location, for example, a certain element will be scheduled, assignment problems, which, let's say, jobs will be assigned to which machines, and so on. Here's an example is given, let's say we want to decide which task is assigned to which agent, and we use the encoding xi. So we have n agents and m agents and n tasks. Then task I is going to be assigned to a certain agent j. So that could be an example of an encoding also. We can also represent this as a binary encoding. If we have, for example, a variable xij that says that is 1 if task I is assigned to agent j, 0 otherwise. So in that case, it's a two-dimensional array. Okay, an example, I think we mentioned this airline flight or crew assignment problem back in the first lecture, where, okay, as an example, we have 20 airline flights and 15 available crews. We want to assign to each flight a crew. We have to have subject to a certain number of constraints. So each airline has to have a certain crew assigned. Okay, in this example, it's not the same number of crews and flights, but that's okay. So a binary representation would be, like I said, x1 xij. So 1 if the flight is assigned to crew j, and 0 if flight I is not assigned to the crew j. Then in this case, we have many variables, which can be easier to manipulate. However, if we look at, and this is a binary representation, if we want to use an integer representation, in that case, we will have fewer variables. But we need to keep in mind then how we're going to design our search algorithm. So how we're going to define these neighborhoods, operators, and so on. In this case, so xi equals to j, as I said, flight I is assigned to crew j. So if xi is, let's say, 3, that means that the value of xi is going to be the flight which is assigned to crew number 3. Okay. Many times in many problems in real life, we actually have to use some kind of real values. So for any type of continuous optimization, let's say some kind of trying to find some optimal parameters in designing some kind of components, or for some kind of simulations, then we need some kind of continuous optimization. And in that case, we usually represent a solution as a vector of real values. And this can also be some kind of a mixture of continuous and discrete values or parameters. Again, this could be one representation of a solution. So each variable is assigned a real value, and then we can define how we're going to manipulate or search this process, the solution space, given certain constraints. Okay, many times we have a permutation vector. So when the solution is represented as a permutation, each element can appear exactly once, such as, for example, a traveling salesman problem where we have n cities. Each city has to be visited exactly once. If we represent our solution as a permutation vector, then, for example, this solution given on the slide can indicate that we're first visiting city 9, then going to city 6, then 8, and so on. Any kind of scheduling problems can indicate, for example, the order in which certain events are going to take place. So let's say we have to schedule these 10 events here in order of time, then this could be a solution to the problem. Any kind of sequencing problems as well. So these are different examples of different linear representations which we can use. Now I wanted to give you an example of a problem where we can see how this choice of representation can actually impact the size of the search space. So how can we reduce this search space? And this is a famous example. So the n queens problem. The goal is to arrange n chess queens on an n times n chessboard such that no queen can attack any other, assuming standard chess moves. So solution for the problem will be the assignment on a chessboard. More concretely, the 8 queens problem states that we need to identify on an 8 times 8 chessboard where to place the different queens so that they cannot attack each other. Okay, so one example of a possible solution is the solution shown on this slide. Now the question is, we want to design a representation that will that we can then use to search the solution space and find all possible solutions to this problem. Okay, representation. Let's look at some variations. So first, if we encode our solution as a vector of 8 Cartesian positions, so each of these elements here indicates the space on the chessboard where a certain queen is located. So each of these can take on, we have 8 rows and 8 columns. So we have 64 possible locations for each queen. We have 8 queens, so that's 64 to the 8th over 4 billion possible solutions. So that's a large search space. If we, of course, we know that we are allowed only 1 queen per row, so we know that we cannot assign, for example, 2 queens to each row. Then we can, what if we specify the representation or the solution representation as P1 to P8? So this is going to be the position or the row in which the column in which the first queen is going to be in row 1. So this is going to be row 2. It's going to indicate which column the second queen is going to be, and so on. This is going to be the 8th row and indicate which column. So we fix the rows, and the decision variables are simply the columns. In that case, we have 8 to the 8th, so 16 million possible solutions. What is another option, a third option to even further reduce the search space? Any ideas? So you guys can unmute since I'm again not looking at the chat.
I think that another possibility is because the direction of the queen is agnostic to rotation, so we can somehow reduce the search space in that way as well.
Okay. Okay. What would be then the size of the search space? How would you represent the search space in that case, or the representation? What would be the decision variables? Any ideas? Okay. One more solution I had indicated here is that, okay, we know in addition to the fact that we can't have each queen can be assigned to a fixed row, we also know that we can only have 1 queen per column, right? So in that case, the encoding is simply a permutation vector, which is going to tell us, okay, for the first queen, we have a choice of 8 columns in which we can put it. Once we have decided on the first queen, the second queen, we have 7 remaining columns left, right? For the third queen, 6 remaining columns, and so on. And we get a search space of 8 factorial, which is 40,320 possible solutions. So if we define our encoding as simply a permutation vector, we get a much smaller search space as compared to this initial search space where we had these Cartesian positions. the point of this simple example is that you really need to consider the size of the search space when you design this representation, because, like I said, a very straightforward, simple way would be to say, okay, I just indicate the coordinates of each queen, but in that case, we have an unnecessarily large search space. Okay, any questions here? One more example I wanted to give in terms of let's say, a non-classical representation, oftentimes used in, let's say, evolutionary algorithms, that actually uses real values to represent permutations. So what's the problem here? When we encode these permutation representations, for example, when we're using evolutionary algorithms where we have some kind of crossover, then we have this problem of feasibility. In that case, let me just go back to this whiteboard for a second. I think I had it over here. Okay, so why are permutations a problem for crossover operators? Let's say that I have a permutation of a vector of 7 values. This is my first solution 1, then I have solution 2. I specify a certain crossover. I get new solutions, which neither of which are feasible, right? Why are they not feasible? Because they don't represent permutations. So one option is to use this random key encoding, in which case we specify certain, so for each position of the variable, we assign some kind of a random key, so a value going from 0 to 1. So if let's say we have four values, 4 variables that we have to decide on, we have to define a permutation of. We simply for each of them, we assign a value from 0 to 1, and we decode them from the lowest value to the highest value. So we have to decode this solution. This is the encoded version, so 0.2, 0.15, 0.10, 0.13. That's an encoded solution in the random key space. We need to decode it. So the smallest value is 0.10. That would be number 3. Then 0.15, that's number 2. Then 1, then 4. So this actually decodes as solution 3214. Our other solution encoded also, we simply assign values going from 0 to 1. We decode it going from the smallest value to the largest value, would give us 3, 4, 2, 1. So in the solution space, these are now our 2 solutions. When we specify a crossover, we use this random key space, so we cross over, we get 0.2, 0.15, and take these 2 values down here, 0.22, 0.26. When we decode this solution, we get 2, 1, 3, 4, which is always going to be a feasible or a valid solution. So this is just an example. Let's go back to the slide, where we use this random key encoding to be able to get to obtain feasible permutations. Okay, this is the same idea just illustrated here. So we have, these are 7 elements. We assign some kind of a random value from 0 to 1. We decode them from ascending, so from the smallest value to the largest value, and look at which elements they represent. So in this case, this encoding here would be decoded as this permutation down here. Okay, any questions here? All right. Okay, an important thing is this representation solution mapping. So we have a certain representation. What is our solution mapping? Is it a 1-to-1, 1-to-many, many-to-1, or so on? So a 1-to-1 solution mapping, we have a certain solution that is encoded, and it is represented by a single, or the encoding corresponds to a unique solution. So there's no, it doesn't represent multiple solutions, so there's no redundancy or space reduction. On the other hand, a 1-to-many decoding means that we have one solution which can be represented by multiple encodings. And an example here, if we consider, let's say, partitioning problems or grouping problems such as clustering, such as graph coloring, bin packing, data clustering, and so on, our goal is to partition a set of elements into mutually disjoint subsets. So for example, if we have a partitioning which we encode as A, B, B, A, so we have 4 elements, A, B, B, A. What does that mean? That means that the first element and the last element and the fourth element are in one group, and the second and third are in the other group. That's the same encoding as BAAB. Right, so it's the same solution, different encoding, but it's the same solution. Okay, that's the case of, for example, many to one, or where multiple, another case would be many to one, where multiple solutions are represented by the same encoding. Let me just illustrate this over here. I drew this over here. So this is, if we look at this representation solution mapping, a one-to-one, this is our problem solution. When we decode it, one-to-one is simple. So there's no each encoding represents a unique solution. These are classical representations. One-to-many, so one solution can be represented by multiple encodings. Like I said, if we have ABBA and BAAB, these are the same solution, but can be encoded in different ways, right? So that's an example of a one-to-many. A many-to-one is an example of where multiple solutions are represented by the same encoder. So we have a certain encoding, but it can represent multiple actually solutions. And the idea is that, and this is also sometimes referred to as indirect encoding over here. The idea is to reduce the search space, but we need some kind of additional decoding function to determine the actual solution. So the idea is to improve the efficiency of the meta-heuristic, but we need an additional step. So we don't have an explicit solution. Okay, let me show you an example of what I mean by that. Indirect encoding is when the encoding is not the complete solution itself. We need some kind of a decoder, which can be either deterministic or non-deterministic, to obtain the final complete solution. So when do we use examples like this? Oftentimes when we have some kind of a heavily constrained problem, such as scheduling, we might use such an example where then the problem constraints are actually handled by the decoder. So we have a certain solution, we can manipulate it, we search the search space and so on, but the actual decoding is needed to get the complete solutions. So multiple solutions can be represented by the same encoding, and we need to decode them to find the final solution. Let's look at an example. Let's take the job shop scheduling problem. I don't know if you've heard of it. So given a set of J jobs, where each job is composed of M operations, these operations are realized on M different machines. So each job has an operation that has to be performed on each machine. Our objective is to find a schedule. So we want to schedule all of these operations in order to minimize total completion time. This is sometimes referred to also as make span. So we want to minimize the make span and determine this schedule. If we look at how we could, or the problem itself, over here we have shown jobs. So we have J jobs, 1 to J, and we have M different operations. What is indicated in this picture? For example, in this first square, this means that so job 1 consists of operation 1. It will be performed on machine 3 in the time interval between 5 and 8 time units. Okay, then operation number 2, also corresponding to job 1, will be performed on machine 6 from, in terms of time units, from 9 to 16, and so on. So this would be an example of a concrete solution to our or direct encoding of this problem. So this would be a solution of the schedule. So we know for each operation that corresponds to each job, which machine it's being executed on and during which time frame. However, if we want to use an indirect encoding, which means that we're encoding a solution, but we need to somehow decode it to actually obtain the final solution. So let's say we have a very simple example, a permutation of jobs. We have J jobs, and we simply find a permutation of these J jobs. However, that is not a solution to our scheduling problem, right? This can be a representation which we're going to somehow manipulate and search and so on. But in order to find the actual solution, we need to somehow decode this. So we need to, if we are given a certain permutation, we need to decode it to create an actual schedule. For example, let's say that if I'm given a permutation like this, I will will create such a schedule that I will always give precedence to operations of higher priority jobs. So let's say they are, we assume this list to be according to priority. So I will take job I, which is first here, and schedule all of job I's operations earliest that I can. Then I will go on to the next job here, schedule all of its operations, and so on. Another example would be, okay, if I take a permutation of jobs where each job appears exactly m times. So we said that each job has m operations that it has to perform. So why don't I just represent this solution as a permutation of j times m? So let's say I will schedule the first operation corresponding to job 1. Then I will schedule the first operation corresponding to job 3. Then I will schedule the second operation corresponding to job 1. Then the first operation corresponding to job 2, and so on. So again, I need this decoder here. I need a decoder that is going to actually derive the schedule in a specified order. And as I said, one example would be to do it like I just said, where you simply go operation by operation and then correspond to each job being considered. Okay, so this was just some examples of indirect encodings, which you can use then to, let's say, reduce the search space or to try to design a more efficient heuristic, rather than starting with a direct encoding and then manipulating this solution which represents the direct encoding. So this is an example, as I said, with the scheduling problem. In addition to the representation of the solution, the next important concept is this definition of this fitness or evaluation function. As I said, this function guides the search and allows us to assign some kind of a quality or fitness value to each solution of the search space. So for S represents our search space. So we have a function, or this evaluation function, that is going to map each of these solutions to some kind of real value. It allows us to rank these solutions in the search space. Sometimes it may be enough just to have information about relative fitness. So maybe we don't need absolute values, but sometimes we are looking at actual absolute values and comparing them. Okay. What is important is that this fitness function is here to guide the search. So we're trying to get to better and better solutions of the search space. If this function is, let's say, poorly specified, then it can also lead to poor solutions no matter what our heuristic is used. Let's look at some examples. On the one hand, we may have a straightforward fitness function, which says that the objective function is also corresponds also to the fitness function. For example, let's say we have the knapsack problem. Again, the knapsack problem, we have each element which has a certain value, a certain cost. We're trying to maximize the value subject to these cost or weight constraints. So our fitness functions for each solution that we have, if I tell you exactly which elements are picked, you can calculate what is the overall value. You can check if it's a feasible solution. So are the cost constraints satisfied? So you can check the value and compare it with another solution and say, okay, is it better or is it worse than another solution? So that's straightforward. Sometimes it may not be so, the straightforward fitness function may not actually guide the search efficiently. What I mean as an example is where we have many solutions which are infeasible and have the same fitness. For example, let's take the satisfiability problem. The objective the objective function has to be somehow transformed. Our objective function is to find a true or false assignment for all variables that will allow for the final expression to be evaluated to true. However, there are very, very many solutions which give me a false false in the end. So function f is composed again of clauses with k Boolean variables. The objective is to find an assignment such that the value of the function is true. If, as I said, I would just take a straightforward fitness function, then which says, okay, the fitness is 1 if this function, my function is true, 0 otherwise, then almost all solutions will have the same fitness value. So the question is, how can I then know, should I move now from one solution to another? In which direction should I continue the search? Any idea how we could modify this? Anyone? So what would you do? How?
What about the
Sorry.
ratio of satisfied clause to the number of the entire number of clauses?
Okay. So I can take two solutions and I can say, okay, in this solution, what is the ratio of how many clauses have I satisfied compared to how many I have versus another solution, and see which has, let's say, which has satisfied a larger number of clauses. Okay, in this example here, we're just looking at the number, so not the ratio, but just the number of satisfied clauses in a solution. So I can say if I have 10 clauses, this solution satisfies 8 of them. Another solution satisfies 3. Therefore, the first solution is better. Okay, that would be, let's say, one guiding fitness function. The max satisfiability problem is a model, is such a model where F is the number of clauses in F which are satisfied by a certain solution. Okay. Sometimes this fitness function or the representation and the fitness function are interrelated. However, sometimes when we look at indirect encoding, the actual representation, and when we use terminology from, let's say, evolutionary algorithms, we refer to this as a genotype, needs to be decoded to generate a best solution or a phenotype. So the phenotype refers to the actual solution that corresponds to that representation. So we need this mapping between the representation and the actual solution. So we need some kind of a decoder function which, given this genotype, will give us the best solution. Again, as an example, and I've already gone through this example of the minimum Steiner tree problem previously, but let me just again refresh your memory. So a Steiner tree, we're given a graph, so it's a non-oriented weighted graph, which with a subset of nodes. So we have a certain graph, with a certain number of vertices or nodes, and E represents the number of edges. So the weights of all the edges are positive. D represents a subset of these nodes, okay, so which are referred to as terminal nodes. And what we're trying to do is find a connected subgraph that connects all of these terminals, okay? So I'm going to take a subset of nodes in my whole graph, call them terminals. They are subset D. And now I need to find a minimum weight connected subgraph that connects all of these terminals. That's the minimum Steiner tree. And I think there was a question going back a couple of weeks where someone asked, isn't this the minimum weighted spanning tree? So this is not. So this problem is NP hard, whereas the finding a minimum weight spanning tree is a polynomial algorithm. So we need to find which nodes are going to be connected in this subgraph, which nodes are going to be included in this subgraph. So we have a set of nodes. So the Steiner nodes are the nodes that are included in the tree but are not the terminal nodes. So I have, let me look at this example here. These are my terminal nodes. So I'm given a graph like this. B, C, and H are my terminal nodes. And my goal is to find a minimum weight graph that connects these nodes. So what I need to do is I need to decide about all the remaining nodes, A, E, D, F, and G, which ones I'm going to include, and in this subgraph, and find this subgraph that is of a minimum weight. One way to represent the solution to this this problem is as a vector of non-terminal nodes. In this case, A, D, E, F, and G. So this is an example of a solution representation. Again, you might have a different representation that includes edges or so on. But this is an example where my solution representation is a non-terminal node, includes non-terminal nodes. 1 if the node is included, 0 if it is not. So if my nodes are A, D, E, F, and G, this solution representation indicates that nodes D, F, and G are included. However, this is not giving me now a complete solution. So the question is, what is my fitness of this solution? What is the solution? In order to obtain the solution, I need to calculate a minimum spanning tree now that includes these picked nodes, so D, F, and G, together with my original terminal nodes, B, C, and H, and I calculate the minimum spanning tree. And the fitness function of that tree is, in this case, 8. Now that's my fitness function evaluation. So I need a decoder function in order to tell me, okay, if I give you this solution, or this representation of a solution, what is the actual fitness? What is the actual solution, the actual phenotype? Are you guys following me in this example? So in order to, if I give you another solution that says I include nodes, let's say A, E, D, and G, what is the fitness of that solution? In that case, to find the fitness of that solution, I would have to calculate a minimum spanning tree of those chosen nodes plus my original terminal nodes and find the weight of that minimum spanning tree. Questions? Is this example clear?
Yes.
Okay. Okay. Just two more things that I would like to mention are in certain cases some kind of or let's say human involvement is necessary in the loop, in this, let's say, loop of designing some kind of a heuristic. Two motivations, or two main motivations for designing something that we call interactive meta-heuristics. First, to guide somehow the search procedure. So in this case, a user can interact with a search algorithm, for example, look at some kind of a graphical representation of solutions and decide on some maybe promising areas of the solution space to check. Also maybe update meta-heuristic parameters. And this is something that's maybe used in most commonly in multi-criteria or multi-objective decision making. Another example is where in certain design problems or so on, we need some kind of a subjective evaluation that depends on user subjective preferences. For example, if you're deciding on, let's say, which web page is more aesthetically appealing or visually appealing, or you're trying to find, let's say, the optimal ingredients in producing coffee. So you have a solution, you have a certain amount of each ingredient. Now, what is the evaluation of this? You need some kind of a human subjective, let's say, input to give you some kind of feedback. So that's what we mean when we say interactive fitness function. And of course, then you are limited in the number of iterations that that you can run in such cases. So where we don't have a simple analytical function, but we have to involve some kind of human in the loop. Okay. Sometimes, as I said, actually, when you design heuristics, oftentimes the actual you find a solution and now you have to evaluate the fitness or the value of that solution. Sometimes that can be actually very computationally intensive. So one thing is that in certain cases we don't need to know the actual absolute value of a certain fitness function. It's enough to know some kind of a relative value. For example, such cases arise when we look at game theory, where, let's say, strategy A is better than B, B is better than C, C is better than A. So actually, there are two alternatives when we look at solving these kinds of problems, either using a relative or competitive fitness. So relative, we associate a certain rank with an individual, let's say in a population of solutions. So we know we can simply rank the solutions. We're not looking at absolute values. Or in terms of competitive fitness, where we look at, let's say, a competition over a subpopulation of solutions, where, let's say, we have tournaments or bipartite competitions or so on. We'll talk more about that when we talk about population-based meta-heuristics. But the point is that here we're only looking at the relative or the competitive fitness and not necessarily the absolute value. One more thing, just to point out at this point, sometimes when you're designing an algorithm and you're computing the evaluation or the value of a certain solution, let's say you manipulate that solution, now you need to find the value of the new solution. Always check if you can reuse, let's say you have a traveling salesman problem, you need to find the overall path. If you going from one solution to another, you simply changed, let's say, a small part of the path. Maybe you can already use part of all previously calculated the previously calculated solution or the value of the previously calculated solution, reuse what you've calculated there and just update, let's say, the length of the path with new information. So the question is, do you need to start from scratch in terms of calculating the value of the solution, or can you already reuse things that you've calculated previously? So that's also one thing to keep in mind. And finally, just to mention the concept of meta modeling, and this is just briefly when we look at, sometimes this actual fitness or objective function is very time consuming, or we don't even have an analytical function that is available. Let's say we have some kind of complex simulation. We're trying to find optimal parameters. Let's say we're designing a network and we want to find some kind of optimal parameters in tuning capacities of the network and so on. We find a solution, but we don't know how good this solution is going to be. We need to run some kind of simulations to find how good a solution is going to be. In that case, we might come up with some kind of an approximate model or approximate solution, or use some kind of machine learning or neural networks to try to approximate, let's say, these expensive fitness functions, where it simply takes too long to calculate the actual value of a certain solution. So just so that you've heard of this concept of meta modeling, that refers to simply approximating this original function, make it simpler to simply speed up the process and guide the search. Of course, this function can be more or less complex, and that will impact the complexity of, or let's say the time in evaluating the actual fitness function. Okay. That's so let's say wrap up there with the slides on some basic concepts. Let's take a break now since it's already, is it 3 o'clock? Yes, it's already 3 o'clock. Let's take a break now, and we can start at 3:15, and then we'll continue with local search and look at some examples of variations and so on. Okay, so let's take a break now, and then we'll continue in 15 minutes. Okay.